would like to introduce the next session, which is focusing on the academic's view on 6G with the speakers, Carles Antonaro and Ton Norp. I would like first to give the floor to Carles, and I will just give a brief overview of Carles' bio. So Carles Anton is with CTTC as the Director of R&D programs and the Senior Research Associate. And he has coordinated more than 80 R&D projects or participated in these through his activity in CTTC and also through the activities of Associated Professor in the University of Catalonia, from where he holds also a degree in telecom engineering and the studies he has performed in Technical University of Catalonia. Thank you, Carles. I give the floor in order to not waste the time. And I will introduce our next speaker right after the speech of Carles. I couldn't hear you, Carles. Sorry. No, I can't hear you.
Can you hear me now?
Yes, that's perfect.
Great. So I was saying thanks for the introduction and thanks for the invitation. So let me share my screen. Can you see it now?
Yes, it's okay.
Good. So let's get started then. So my talk today is, as you can see from the title, it's about 6G radio interface design, which is my area of knowledge. And specifically, I will comment on what I think are the key enablers for such a radio interface design and the role to be played by artificial intelligence in this process. I will try to provide an academic view, even if CTTC somewhere sits in between academia and industry, but well, I will try to play this role today. So let me show the agenda for today. First, I will briefly comment on, the new use cases and the technical requirements associated to them for 6G. I will quickly go through this. And just to motivate that, well, there is a need for additional enablers to properly design those 6G radio interfaces. And next, I will comment on, as I anticipated from the title, what is the role to be played by artificial intelligence in this process, and provide some specific examples on how to do that for physical and link layer technologies in order to finally draw some hopefully meaningful conclusions. For the use cases, let me use this white paper by ITU, very recent one. Out of those new use cases for 6G, there's holographic communications, which can be used for media, for improved e-health or remote monitoring services, for Industry 4.0, remote education, for troubleshooting as well. And the challenge here is that those holographic communications require the combination of very high data rates in order to properly transmit each of those individual flows that constitute the holographic image, and also with very tight synchronization among them. That means that the latency has to be very low, on the order of some milliseconds, and so has to be delay jitter. In particular, when combined image and video combined with other information on other sensors, it's running on their own flow. Next, another typical paradigmatic use cases for 6G is the tactile internet for remote operations. That is a combination of closed loop control with real-time audio and video monitoring in combination with very low latency feedback channels. This can be used, for instance, to operate industrial machines remotely, like you can see here, or in order to do some surgery. In this case, of course, latency is critical. So is reliability, in order to make sure that this control is done in a proper manner, or that the surgery goes in the right direction. Reliability has to be very high, on the order of 5 nines or above, and also sub-millisecond latency for the instantaneous haptic feedback that is needed to do those tasks. Some additional use cases. Well, connectivity for everything. It's not about interconnecting a handful of sensors, but to do that in a massive manner with buildings, cities, cars, other critical infrastructures that need to be protected, also with devices that we wear on our body and inside our body, or meters for water and power supplies, just to give a few examples. This means that the device density will increase dramatically, and this goes well beyond what can be achieved with 5G massive machine type communications. Since the number of devices is high, so will be the aggregated data rates. And in some cases, for instance, for medical information, security and privacy concerns are key for this use case. And finally, since 6G networks will have to cope with increased flexibility to accommodate different services, different SLAs, and also complexity because of the sophisticated technologies that will have to be used. Most of its operation will have to be done in an automated and intelligent manner. This means closed loop control loops again, where both the collection of data, also the analysis, mostly based on AI techniques, and also the return control channel, in order to actuate on the network, have to be of very low latency, on the order of milliseconds or sub-milliseconds, and in some cases even high bandwidth, in order, depending on the nature of the information to be collected from this network. This means that well, those use cases, we also only saw a small sample of use cases, of course, lead to very challenging requirements and KPIs, even if still KPIs are still under definition, as the previous speaker commented a few minutes ago. Some figures start to be on the table, like peak rates on the order of terabits per second, user experience rate, that is, say, for the vast majority of users in the system, on the order of 1 gigabits per second, sub-millisecond latency, high mobility on the order of 1,000 kilometers per hour, in order to for 6G systems to be used also on board in planes, for instance. Increase in network efficiency, increase reliability, as I discussed a few minutes ago, and also increase device density, number of devices per square kilometer. When compared with, say, those KPIs that were used for the design of 5G, this means, well, a substantial, in some cases even dramatic increase of their, say, of those KPIs. For instance, a 50-fold increase in terms of peak data rate from 20 gigabits per second to 1 terabit, 10-fold increase in the user experience rate, 10-fold increase in the number of connection density, 10 to 6 to 10 to the 7th power, and also mobility has to cope system has to cope with higher terminal mobility, up to 1,000 kilometers per hour. Just to give some examples, of course, other figures or similar figures can be found in other references. Here's a table from these 3 white papers. Here you can find the references at the end of the presentation, also from this other reference, and some additional data here in the form of a spider web that was used for the 5GIA white paper on 6G that was recently released in June this year, where you can see this spider clearly exemplifies that the requirements for 6G systems, KPIs, will go far beyond those of 5G, which are given by the blue card, with increases or decreases which are as high as 10-fold or even 300-fold in the case of energy efficiency. What does it imply? Well, that 6G network will have to deal with more challenging applications like holographic telepresence, also meet far more stringent requirements like the ones we commented a few minutes ago. And it's not only that they are more stringent, but for specific use cases or services, some combinations of those KPIs will have to be, say, fulfilled or satisfied by the underlying networks, not all of them to the maximum values, but for instance, 1 terabit per second with, I don't know, 10 millisecond latency. That could be example for a given use case. This calls for an in-depth redesign of the radio interface because 5G radio interfaces are relatively far from those KPIs. How can this be done? By going higher in the carrier frequencies, sub-terahertz, terahertz, or up to visible light communications. The network infrastructure necessarily has to be more dense. For instance, adopting cell-free network paradigms. This will make it possible to have a larger spectral efficiency per square kilometer. Also, distributed processing, leveraging, for instance, on multiple access to take computing closer to the end devices and making end-to-end latency lower. And also combination of terrestrial and satellite wireless networks in order to ensure ubiquitous coverage. So what do we need to satisfy those trends? Well, here is, of course, a non-exhaustive list of enabling technologies that were distilled from those white papers here and also from my own research work. Here's the list, which is quite extensive, but I will comment on them very briefly on the next slides. When it comes to terahertz communications, these are very valuable because huge amounts of spectrum is available on those bands. This means that you can go for higher peak data rates, for instance. But of course, this comes with some problems in terms of hardware implementation constraints and also the need to mitigate some nasty effects like phase shift in higher frequency bands. Channel modeling the terahertz frequencies is not as well known as in lower bands, of course, and some research is needed there. Optical wireless communications can also be very helpful, be it in the infrared or in the visible light spectrum bands, for instance, for backhauling or for broadband local connectivity. The advantages there is that even bandwidth is even higher there, the available bandwidth. There can be a special confinement because of those beams are, restricted to home environments, for instance, and there is no leakage outside, which make them inherently secure. There are some difficulties because unlike in RF systems, there's this positive value amplitude constraint for visual light communications, for invisible light communications, for instance. So it's not straightforward, the application of the RF technologies to VLC. And of course, they are subject to optical blockage. For instance, if you put your mobile phone inside your pocket, the party is over. Other enablers, ultramassive MIMO and holographic radio. Massive MIMO is already there in 5G with antenna arrays on the order of tens of antennas, but it's about going to, say, thousands of antennas in 6G. This means that we will move from a beam sprays approach under the assumption of far field communications to a different, say, paradigm where there is scattering because signals are operating in the near field. And then we are going to holographic radio spaces where there are no beams, but radiation is, say, concentrated in specific points in the 3D space, thanks to interference of radio wave signals. If we go higher in the frequency, this means that the implementation complexity grows as well. But well, there's no free lunch. There's some price to be paid. Self-free networking, as you know very well, it's about going from, say, few access points with a very large number of antennas to an increased number of access points interconnected with backhauls to the central processing unit and fewer antennas per access point. This means that well, each user equipment is served not but a lot of antennas, but a few ones which are good because they are nearby, and this allows to increase the rate for a majority of users, not the peak rate, but the rate for the majority of the users, like 95% or something, that are camping on the cell. This also allows for lower latency because content can be cached closer to the user equipment. But well, some redesign is needed for initial and random accesses, for instance, because UEs will be connected to multiple access points. What else? Intelligent reflecting surfaces made of metamaterials with their, say, electromagnetic properties can be controlled without RF change. This is important because we are going up in the frequencies and it's difficult to accommodate RF change there. And also it has the advantage that the cost will become lower because there are, as I said, no RF change. And so can be complexity and energy consumption. This allows to introduce some additional scattering, which is very much welcome in terahertz frequency because it's lower there. and also allows to overcome blocking situations in non-line of sight condition by taking additional paths from the transmitter to the receiver when the direct path is blocked, for instance. This adjustment of the intelligent reflecting surface can be done even on a standalone manner that is transparent to the wireless network, or be jointly optimized with the transmitter and receiver strategies. What else? Another key enabler would be positioning, sensing, and communication in an integrated manner. In this way, we avoid having an additional system for localization. The challenge in 6G is to go down to centimeter accuracy, and also allow to detect objects like other cars or other elements blocking the road in a radar like approach. And to that aim, either we come up with novel waveform design, which are valid both for communications and for sensing and localization, or we do our best to try and multiplex communication signals with other signals, for instance, chirp signals, which are more useful or more amenable for localization tasks, for instance. Or we can also leverage on massive MIMO antenna arrays where they are available in order to use them also for sensing tasks, because they have, say, higher angular accuracy, for instance. And finally, well, it's also welcome enhancements to the modulation and coding schemes. For modulation, probably one size will not fit all. We will need single carrier for higher frequencies where we have larger phase noise, and single carrier is less sensitive to that, to multi-carrier approaches, which on the contrary have better spectral containment properties and are easier to handle for scheduling users. And there are also other approaches coming up, like orthogonal time frequency space, that allow to exploit frequency spread in order to multiplex in the delay and Doppler domain. Coding has also been improved, because in order to go with gigabit per second throughput, either we have the coding schemes that converge faster, or can be parallelized in order to reduce their runtime, their execution time. And also we should keep an eye on energy efficiency and cost considerations, while ensuring low error floors and sharp waterfall regions in order to meet reliability requirements. Finally, other multiple access techniques like NOMA, which is suitable for a large networks with massive number of terminals under a gram-free multiple access scheme, will be very welcome. And also rate splitting, which this allows us to dynamically manage interference, which can be treated as noise in some cases for successive interference cancellation detectors. And very quickly, as for the role of AI in 6G radio interface design, let me comment you a few ideas. First, well, as I said, there are a number of sophisticated technologies that are being introduced for 6G networks, like the ones I've just discussed. This is good because user experience can be enhanced, but networks become more and more complex to manage. And this is only can be done automatically and not manually, in order to better exploit the available resources. This is where AI and ML have a role to play, a pivotal role to play, I would say, specifically where there is a model deficit, for instance, to design receivers when there is no channel model, for instance, for higher frequencies or optical wireless communications, or algorithm deficit, where it's too costly to solve the problem, or it simply cannot be, there is no, say, a given solution for a specific time frame, timely solution. Still, for radio interface design, we advocate for hybrid approaches, combining both data-driven ones, AI, and also model-based ones, the traditional ones, leaning and leveraging on decades of signal processing and engineering know-how, because this can be particularly useful for designing enhanced functionalities at the physical and link layer, and still being able to provide some performance guarantees, which cannot be often guaranteed by data-driven schemes. Just a few examples about what can be done at the physical and link layers with AI ML. For instance, we can think of channel decoding schemes based on deep unfolding strategy, that is by replacing iterations in the coding schemes with a number of layers in neural networks. Can also be done for channel estimation and without pilot symbols. You save the pilot symbols. This can be done by inferring the uplink channel from the downlink measurements That means that no additional pilot symbols are needed for the uplink, and this can be done again with neural networks in order to estimate the channel in a given location for a given set of frequencies from the measurements, the channel measurements in other locations and in other frequencies that can be found in self-free or distributed MIMO systems. They can also be done, but can be used for user clustering in MIMO-NOMA schemes, that is in order to group all the users in a cell that will be sharing the same orthogonal resource like a beam or frequency or time slot. This is a combinatorial problem that is an algorithm deficit, which can be overcome by using unsupervised user clustering schemes, or for beam prediction and selection in coordinated and hybrid beamforming. Here, the case is avoid, say, exhaustive searches in order to determine what is the optimal beam to be used by, say, exploring them in a sequential or a hierarchical manner, and instead do that one shot. That is, train a neural network, measure the channel, and within one shot determine what is the best beam to be used. Well, and this concludes my talk. Just to sum up, we have seen that, well, the new use cases for 6G are pushing KPIs, or at least tentative KPIs, to the limit. This entails an in-depth redesign of the radio interface. To do that, you need to use some key enablers and to carry out research in those enablers in order to tune them and to improve them and to be able to use them in 6G radio interface designs. AI/ML is expected to play a pivotal role there to deal with increased complexity and automation level. And for the PHY and link layer functionalities, we advocate for hybrid approaches, not entirely or purely data-driven approaches. And we have also identified some examples for radio interface design in terms of channel decoding, channel estimation, user clustering, and so on and so forth. And this concludes my talk. Thank you very much for your attention.
Thank you, Carles. Thank you. Very interesting. You have covered a lot of topics in a few minutes. So I would like to go to the next speaker from TNO, Mr. Torn Nor. He's a senior business consultant at TNO. He has joined since 1991, and he has been working on network aspects of mobile communications. And he has also been strongly involved in standardization efforts. And he has served as chairman of the 3GPP SA1 Service Aspects Working Group, which was responsible for the building of requirements and the specification of the requirements for 5G. And recently, he has also been involved and elected as board member of the 5G IA, the Infrastructure Association. Tom, we look forward to your speech. Welcome. You can share your screen.
Thank you very much for the introduction. Can you see the screen?
Not yet.
It should be. Oh, wait, sorry. I need to press one more time.
It's coming. It's coming. Thank you. Yeah, we can see it now.
Okay, so thank you very much. Also, Carl, thank you very much for some introduction that I can use very much in my presentation. Before I go, what I want to do is to give a TNO view on 6G, and I have selected a few specific topics that I want to discuss. There's much more in TNO view on all kinds of topics for 6G, but this is a specific set of aspects that I want to cover. Before that, first, a very little bit of background about TNO. TNO is a Dutch independent research organization for looking at applied science. In total, about 3,500 employees, but that is a lot of different kind of topics. I think there's about 300-400 people that are working in the information communication technology where I am working at. And within that, I work in the networks department where we are considering radio access, cloud infrastructure. So we have our own research cloud infrastructure, and we're doing research on that. And we have mobile networks that are running in this cloud-based core network. Cloud-based core networks. We have core networks that are running in this cloud infrastructure. And we're doing also research on that. So if we look at 6G, well, of course, sixth generation, yeah, what we see is clearly that we are getting more and more data each generation, from going from all the way to the left where we had car telephony with just voice, and then we have more and more video, text becomes video, video becomes VR, and in 6G we are expecting holographic kind of applications. One of the things is that it's more and more data, but you can also see that the applications that we're using with this are going to be more and more indoor and more confined. If you look at the 1G car telephony, that's for people that are driving around in cars. So you need to have good coverage everywhere on all the roads. But this holographic presence is not going to be everywhere. This is going to be mostly indoor. So we see a little bit of a move from the earlier generations, which were very much on trying to cover the people that were on the move outside, to supporting applications like AR, VR that are actually inside. People are going to be inside their home when they're doing AR, VR gaming, or in this case, this is a holographic surgery that, of course, is also not quite somewhere on the road that happens. So we get a bit of a challenge because on the one end, we see that these high data rate applications are mostly indoors. And on the other hand, we see that for these higher data rate and higher capacity, we need to go to higher frequencies, to, for instance, terahertz frequency bands. But there we get the problem that propagation at these high frequencies is a challenge. If you want to, as was said before, if you put up your hand, then the radio propagation is changed already. So how are you going to do this when you have a building or a house with different rooms? You're going to need to assume that you have indoor base stations, because I think it's going to be very difficult to go from outside to inside at these kind of high frequency bands, and not just from not just a indoor base station, but many base stations inside, with probably base stations per room. So you have a very, very dense network with a very highly dynamic environment. Somebody walks through the room and your radio environment changes. And we think that this is, as Carl also was indicating, we're going to need AI and ML-based resource management to deal with this kind of situations. Self-networking and maybe ultra-massive MIMO beamforming can help a bit to get the propagation throughout the house, let's say to get radio coverage throughout the house. But still, we think that there will be a lot of base stations needed. One more thing, sorry, I'm forgetting one thing. If you look at this indoor challenge, then also we have to see 6G, but there's also Wi-Fi. So what is the relation going to be between 6G and Wi-Fi when we are talking about covering indoors environments? The next topic is 6G design criteria as TNO sees them. Energy efficiency is going to be crucial, as was also shown in this spider web that Carl showed. Over, let's say, going from 5G to 6G, we will probably see another 300 or 500 or maybe 1,000 times growth of the amount of data. If we don't have a energy efficiency increase that is at least the same, we will need to spend a few hundred times more energy in mobile telecommunications than we are doing now. That is completely impossible because there is not that much energy around, and we want to reduce the amount of energy because of the climate change. So we will need to have a very massive growth of energy efficiency, both in the energy per bit transported, but also in the energy per device or the energy per base stations. If we don't do this, then it will not be sustainable. And I think this is one of the biggest challenges that if you look at the KPIs that need to be improved, then energy efficiency is one of the KPIs that needs most work. Another design criteria that we see is 6G needs to support resource sharing. Now it's quite common that every mobile operator has their own network, has their own frequencies, has everything on their own. But if you start to go into ultra dense networks, go into people's houses, go into offices, etc., then this is no longer sustainable. You can't have in let's say in an apartment building indoor in every room 4 different base stations because there are 4 different operators. You have to do things more in a shared way. And that needs to be supported by the 6G infrastructure. Integrating sensing and communication. I think that this was also mentioned a lot of times. I think that it is interesting to see that this provides, on the one hand, new kind of services. We have in 5G, we see an increase of localization that provides a lot of opportunities, localization. But I think that with sensing and cognition, you start to get even more things. Let's say if my house can sense that I'm there, that maybe I'm in a bad mood and I want to do something, then this is something that already can be taken into account by a virtual agent that controls or assists me in my life. This is something that we think that will happen more. It can also help with optimizing the radio environment, sensing where things are and using that. Yeah, and then we think that radio becomes AA native software in an open architecture. So we think that more and more all the radio algorithms are going to be implemented in an open cloud infrastructure, similar to what we now have with core functionality in the 5G network. And basically, we end up with a software-based implementation that can flexibly be updated. We don't have to wait for the next generation, but we can just have the next software version installed for a newer or updated radio technology, or for all kinds of functionalities that can be in this implemented in this cloud infrastructure. So much more flexible evolution because everything becomes software. Connected intelligence. This picture, I think Bernard Barani this morning was also showing it. This is what we created in the 5G PPP white paper. What we see is, on the one hand, we see twinning, so digital or virtual representations of things in the physical world. There's an example that I've heard from a car company in Aachen, where they record, for instance, the torque that is used to tighten the nuts on a wheel. And all this information is stored in the digital twin for the car. So next time the car arrives at the garage, then the garage owner can already see what torque was being used, and all this information is stored in the digital twin. So the next time the let's say maybe the wheel is undone, the torque wrench again will record the torque that is used, and again this will be also stored in the in this virtual twin. Also for the human world, we think that we get more virtual representations. Now everything is based on a mobile phone. My mobile phone represents me, and that's what I use to communicate. But maybe in future I can use all kinds of different devices. I can use my laptop, I can use my iPad, I can use my mobile phone, but I can also use a TV screen that is hanging somewhere in a meeting room in my office, or maybe other sensors can see things about me and can take that into account when, for instance, somebody wants to send me a message and they can see that, oh, well, actually, he's asleep. We can sense that because he's in his bedroom and the lights are off. Okay, so don't disturb him. That's another way of sensing, of cognition, and all that will be represented in a digital representation or a virtual agent that is running for me. Now, the interesting thing becomes if we have to, first of all, scale for all these virtual representations, because there is going to be an enormous amount of virtual representations. Each of them are relatively small, but you need to have a cloud infrastructure that can deal with all these different virtual representations. And they also need to be identifiable, because now if I want to, for instance, go tomorrow morning to a meeting, my virtual agent is going to talk to the digital twin of my car to see if it is charged. And that needs this connected intelligence, that needs communication between different kinds of virtual agents and digital twins in the cloud. And where now a mobile phone is talking to another mobile phone, and the mobile phone is identified by a SIM card, talking to another mobile phone also identified by the SIM card. Now we have things in the cloud that are talking to other things in the cloud that also need to be identified and authenticated that actually I'm talking to the right car and not to somebody else's car. This may have an interesting impact on how mobile networks are designed. So, in conclusion on these few topics, some bold statements. I think that if you look at this big focus on providing something for indoor communications, we may not have a room for both 6G and separately new Wi-Fi technologies. Maybe like we've seen before, where, for instance, Tetra for public safety was now integrated into mobile telecommunication standards. Maybe this also needs to happen with Wi-Fi, that there is just a single technology for indoor communications at these very high data rates. If we do it right, 6G can be the final generation. That's related to this everything software on an open infrastructure. We either had, let's say, going from one generation to another generation, we had either a new core network or a new radio interface or both, with a infrastructure that is fully cloud and software and open. Then we can just have piecemeal upgrades of smaller software components, and we don't need really big steps in generations anymore. And I think that 6G can be the death of the smartphone nowadays. At least in 4G, everything is based on smartphones. That's the way you talk with the mobile network. But I think that in 6G, you will have a whole bunch of devices and capabilities to interact with the digital world. And it will not be just one device that is used for that. There will be a whole bunch of different devices and sensors, etc. That concludes my presentation. And there's here the link to the white paper, the 5D PPP white paper. Thank you.
Thank you, Ton. Thank you, Carles. We have received no questions. And in fact, we have accumulated some delay in our program. I thank you both for these very interesting presentations. I think we have covered almost all the topics that we were expecting to hear. Thank you for that.